So the title of today's lessons is Operations with Rational and Irrational Numbers. Go ahead and take a minute and put that on the top of your page in your notes along with today's date. So in pre-algebra, we do not have to know how to solve problems with rational and irrational numbers, but we do have to know whether the answer is going to be rational or irrational. So really all we do is classify a problem. Specifically, we stick to addition and multiplication of rational and irrational numbers and whether or not the solution to those problems would be classified as a rational or irrational number. It often makes sense to actually think about how you would solve the problem in order to classify the answer. So as we look at classifying these solutions, we will also look at the answers, or really not so much the answer as just what the answer could be in the process of solving it. Sometimes we will do the answer, and sometimes we'll just get really close to the answer to think about whether or not it will be rational or irrational. So the first set of rules that we're going to look at are called the always rules. And again, remember, you should not be writing while I'm talking. I will have the substitute pause the video after we've discussed it and give you an opportunity at that time to write. Right now, you should be listening so that you understand what it is you're writing in your notes. A lot of times when you're writing at the same time that I'm talking, you are not able to listen and really understand what is being said. So the first problem I want you to think about is when you're adding two rational numbers. So if I add two fractions, we know the answer is a fraction. If I add a fraction and a whole number, we know the answer is a mixed number. If we add two whole numbers, we know that our answer is a whole number. So anytime you're adding two rational numbers, your answer is always going to be rational. The example here is a half plus the square root of 16. And you can go ahead and just think about how you would solve that. We know the square root of 16 is 4. The order of operations tells us to solve that first. So then we have half plus 4. And we know that that's going to give us a mixed number. And we know that a mixed number is a rational answer because if it can be written as a ratio, as a fraction, it's considered rational. So there is never going to be a time where you add two rational numbers and the answer is not rational. It is always rational. On the same note, if you are multiplying two rational numbers, a rational times a rational is also always rational, unless the denominator of the fraction is 0 and then it's undefined. And really, I don't even think this needs to be put in here because if you have a fraction with a denominator of 0, that's not a rational number. Right away, we know that that's not even a real number, so it's not classified as rational or irrational. So if one of your problems or add-ins in your addition problem or factors in your multiplication problem is unreal, then it's not a solvable problem. The entire problem is unreal or undefined. So in this example, we have the square root of 9, which is 3, times the square root of 5, which is, 25, which is 5, which gives us 15. 15 is a whole number and 15 is rational. Same thing if you had a fraction. So say you had 1/2 times 1/4. We know that we can multiply fractions times fractions to get a fraction. And your answer is always going to be a fraction, so it's always considered a rational number. So anytime you multiply a fraction times a fraction, it is always going to be a fraction. So anytime you multiply a rational times a rational, your answer is always going to be rational. Adding two rational, it's always going to be rational. Multiplying two rational, it's always going to be rational. So far, I feel like this is pretty basic And you guys probably already know this, you just haven't really talked about it in terms of rational and irrational. So now let's kind of add in the irrational part, because this is where sometimes it can be a little bit confusing because irrational numbers are newer to us and we've been solving problems with rational numbers all the way through to pre-algebra. Pre-algebra is probably the first time where you will start to see those irrational numbers. So here you have 4 plus pi. Now, we can round pi to 3.14, but we know that that is a rounded number. So I cannot write out the true value of pi because it would go on and on and on. So instead, I'm just going to write out, just so that you can see that the answer is going to be irrational, I'm going to write 3.14 ... And that just shows that that is a rounded number, it continues. So if I were to line these decimals up and add these whole numbers, I'm going to get 7, but this non-terminating decimal is still always going to be part of the answer. So it's still going to be 1, 4, ... I am always still going to have that non-terminating decimal as part of my answer. Once a non-terminating decimal, always a non-terminating decimal. There's nothing that I can do to change that. So if I add another whole number to it or another fraction to it, it's still going to be a fraction and a non-terminating decimal, which means the answer is still going to be irrational. Always, 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 always. So remember, all of the ones that we're looking at right now is always rules. There's never a time that it's going to change. There's never an instance where I can add a rational and an irrational number and the answer not be irrational. So now same thing with multiplication. We're going to look at multiplying one rational and one irrational. So again, you're always going to have an irrational number. There is one small exception here. When you multiply by 0, remember 0 is a rational number. If you multiply an irrational number, a non-terminating decimal, by 0, it will void out that non-terminating decimal. So the square root of 7 is a not perfect square root, so it's going to give us a non-terminating decimal. But then when I multiply it by 0, this 0 is going to get rid of this non-terminating decimal, because we know that anything times 0 is 0. So this answer is 0, which is going to give us a rational answer. That's the only time. Other than that, here we have the square root of 5, which is a non-perfect square root. So that is going to give us a non-terminating decimal. And then the square root of 16, which will give us 4. So if you have 5 and you find the square root of 5, I'm going to round it, and I'm just going to put dots. It's going to give us approximately 2.236 ... And again, those dots just show it's non-terminating, times 4. And I'm going to multiply that, and you can get your calculators out, and you can actually multiply it out on your calculators, and you'll see that it's always going to give us another non-terminating decimal. 9, 4, again, ... This is actually not something that you have to know for my class, but it's actually pretty easy to go ahead and explain it. So when you have two square roots that you are multiplying, you can actually multiply those square roots. So the square root of 5 times the square root of 16 is actually the same as the square root of 80. And so if you were to type in the square root of 80 into your calculator, you would see that it is a non-perfect square root, and it also gives us the same solution to the above problem that we just did. It's 8.94 ... It is a non-terminating decimal, and that's just another way to see that the answer for a rational times an irrational is still irrational. And it will always be irrational except when multiplied by 0. So at this time, the substitute is going to pause the video, and you guys are going to take about 10 minutes to probably copy all of these rules in your notes, and some examples for each rule. And feel free to add any of the math on here that I also added into the notes that would help you understand it when you go back. I also recommend maybe taking a highlighter and highlighting these 4 rules so they stand out among the examples. So I would highlight what I have underlined on this slide. I would probably highlight that in my notes so it just kind of pops out those rules. I would write the word always at the top of these rules, just like I did in the notes. Really big, all capital letters, underline it, make it stand out. So you know these are your 4 always rules. And make sure you have this one exception to the always rule very clearly done in your notes. And then when all of you or the majority of you are done getting this in your notes, the sub will come back and press play, and we will look at the sometimes rules. So if you think about what we've looked at so far when we looked at our always rules, we looked at when we had 2 rational, adding and multiplying, and we've looked at one of each, 1 rational and 1 irrational, adding and multiplying. Now, when you start to look at 2 irrational is when sometimes it can be a little bit tricky. And so these are what I call the sometimes rules. Sometimes when you are adding 2 irrational, the answer is rational. And sometimes when you are adding 2 irrational, the answer is irrational. So sometimes the answer can be rational and sometimes it can be irrational. It can be either or. And the same goes for multiplication. So when you are multiplying 2 irrational numbers, sometimes the answer can be rational and sometimes the answer can be irrational. And the best way to think about this is thinking about what I did on the previous problem where I multiplied the square root of 5 times the square root of 16. If you understand that you can multiply the square roots before solving the square roots, it will help us understand when it's rational and when it's irrational. So we're actually going to talk about multiplication first, and then I'll go back and talk about addition. So let's look at some examples together. If you think about factors of a number, if I multiply 2 non-perfect square roots that are factors of a perfect square root, then the answer is going to be rational. So think about it like this. I know that 6 times 6 is 36. So the square root of 36 is 6. So if I have 2 non-perfect square roots, 6, the square root of 6, times the square root of 6, those are 2 non-perfect square roots, which means they are 2 irrational numbers. I am multiplying an irrational times an irrational. But we know that we can multiply both of these numbers before we find the square root. So instead of finding the square root of 6 and the square root of 6 and then multiplying it, I can multiply 6 times 6, which gives me the square root of 36. The square root of 36 is a perfect square root. So when your non-perfect square roots are factors of a perfect square root, then your answer is going to be rational. So in this case, you have the square root of 6, irrational, times the square root of 6, irrational, giving you the square root of 36, which is, yes, you've got it, rational. So it's pretty easy if you know your perfect square roots, because if you know the square root of 25, you know that the square root of 5 times the square root of 5 is going to give you the square root of 25. So it's really easy to find a bunch of these problems just by using your square roots. So square root of 5 is non-perfect, irrational. Square root of 5, irrational, equals square root of 25, which is rational. So this is pretty easy, but there are other ones where your 2 factors are not the same number. So if you go back to 36, forget about the fact that they're square roots and just think of your factors of 36. You've got 4 times 9 but 4 and 9 are not irrational. If I do the square root of 4, that's a perfect square root. So that doesn't work for this example. So we want to find different factors of 36. So I've got 4 and 9. I've got 6 and 6, which I already did. What about 12 times 3? 12 times 3 equals 36. And the square root of 12 is an irrational number. And the square root of 3 is an irrational number. So you can use other factors. You don't just have to use the same factor to get that square root. So I could do the square root of 12 times the square root of 3 equals the square root of 36. So this is another example that's slightly different than the square root of 6 times the square root of 6, square root of 5 times the square root of 5. But the square root of 12 is irrational. The square root of 3 is irrational. And the square root of 36, we know, is rational. So these are other examples. Oops, that's 6, not 5. Sorry about that, guys. I was thinking about the fact that I didn't put the previous answer, and then I put the wrong answer for this problem. So, again, we have irrational times irrational. All of these examples so far have been rational solutions because it's easy to see when they're rational so that you know when it's not rational or when it's irrational. So, for example, if I have two square roots that are not perfect square roots, that are irrational, say 3 times the square root of 7. So the square root of 3 and the square root of 7 are both non-perfect square roots, so they're both irrational. And when I multiply those, it's going to give me the square root of 21. 21 is not a perfect square root, so this is an example where when you're multiplying two irrational numbers, the solution is also irrational. And then we could do another example. Again, I'm thinking of my perfect square roots. I'm thinking of, let's do 16. And so I know my factors of 16 are 4 times 4, but 4 is perfect square root, so that doesn't really work. So we could also do 2 and 8, and both 2 and 8 are non-perfect square roots. So the square root of 2 times the square root of 8, that's irrational times irrational equals the square root of 16 rational. So you see sometimes when you're multiplying two irrational numbers that sometimes our answer is rational and sometimes our answer is irrational. So let's talk about addition. Addition of two irrational numbers is much easier than multiplication because there's only one instance where you can add two irrational numbers and get a rational answer. And so for this example, you need to think about making zero pairs essentially, except we're making zero pairs now with irrational numbers. So before we throw in rational or irrational, just remember what we learned with zero pairs. So if you've got -2 and +2, these cancel each other out and we've got 0. So now if I make these square roots, if I have the square root of 2 negative, remember the negative has to be outside, it's undefined if the negative is inside, plus the square root of +2. So whatever this answer is, it doesn't matter. I mean, you want to use your calculator and figure it out. It's probably close to, well, let's not do close. Let's go ahead and get out our calculators and figure out. I'll go ahead and type in 2 and I'll square root it. So it's approximately negative 1.414 ... plus, and then here it's the same thing except there's no negative. So if you see and you think about what we did with zero pairs, when you are adding two irrational numbers, that are the same quantity, 2 and 2, or negative 2 and 2, then these will cancel each other out and make those zero pairs. So this answer is going to be 0, and we know that 0 is a rational number. So this is irrational plus irrational equals rational. This is the only time you're going to add two irrational numbers and get a rational answer. If they do not cancel each other out by making zero pairs, then it's going to be irrational for every other example. So at this time, the sub is going to pause the video, and you are going to put this in your notes, making sure that you have the title sometimes in all caps and underlined so it stands out. And then there's examples down here of showing how they cancel out when you're adding two. And there's also an example where this is a non-perfect square root that gives you the square root of 15. And here we have the square root of 25 times square root of 25, square root of 5 times square root of 5, which gives you 20 square root of 25, which is 5. And we can also add in, I'll have the sub go back and pause it for the other problems that we did after you've written this in. So if you want to add in some examples from the other slide, I'll put that in at the end and you can pause it again. So now we are going to do some practice problems. You guys can go ahead and take a minute and quickly get out your socks and markers. And what we are going to do is the same thing that we did on the previous lesson. I'm going to explain the directions, and then the substitute will pause the video, and you guys will try number 1 on your desk. And when the majority of you have finished the problem, the substitute will pause the video, and I will explain number 1. And then she will pause the video and everybody will try number 2. And then I will explain number 2. And then she'll pause the video and everybody will try number 3. And then when everybody's done, she'll press play and I'll explain number 3, and so on and so forth. So you are not actually solving the problems. You are simply telling whether the solution to the problem is going to be rational or irrational. However, sometimes it will help you if you actually start to think about how to solve the problem in order to determine if the solution to the problem is going to be rational or irrational. So go ahead and try number 1 on your desk. So assuming that everybody's had a chance to try number 1, let's go ahead and work it out. Number 1 is the square root of 6, which is a non-perfect square root, plus square root of 5, which is a non-perfect square root. So what we're doing here is we are adding two irrational numbers. And the only time that we add two irrational numbers and it's rational is when they make a zero pair. This does not make a zero pair, which means the solution is not going to be rational, it's going to be irrational. Go ahead and pause the video and try number 2. Number 2 was a lot easier. Number 2 is the square root of 16, which is 4, perfect square root. So it's a rational number, plus 5, which is also a rational number. So we have a rational plus a rational, and remember that's an always rule. Whenever you add two rational numbers, you're always going to get a rational number. And you don't have to tell me the solution is 9, but like I said, sometimes it does help to start working it out, especially on these problems that I know you know how to solve. And so the answer to number 2 is rational. All right, pause the video and try number 3. Number 3 is also pretty easy. You have a third, which is a fraction, so it's rational, and a whole number 7, which is also rational. So you have another rational plus rational, just like number 2. So we know that when you add two rationals, it's always going to be rational. So you have 7 and 1/3, which is a rational number. Again, you don't have to give me the answer. You just have to classify the answer but sometimes it helps to go ahead and work it out. Try number 4. Pause the video and try number 4. So on number 4, you have 2 irrational numbers like number 1. The only difference between number 1 and number 4 is number 4 does make 0 pairs. So you have negative square root of 6, which cancels out adding the square root of 6. These make 0 pairs, so my answer is 0. And we know 0 is a rational number, so number 4 is also a rational number. So 1 through 4 is all addition, and 5, 6, and 7 are all multiplication. So let's try some multiplication. Go ahead and pause the video and try number 5. So number 5 is a little bit tricky. We do have the square root of 2, which is a non-perfect square root. It's irrational. And the square root of 32, which is also a non-perfect square root. But these are factors of 64. When you multiply 32 times 2, you get the square root of 64. And 64 is a perfect square root. It is 8, which makes number 5 a rational solution. Pause the video and try number 6. So again, we are multiplying 2 non-perfect square roots, 2 irrational numbers, square root of 8 and the square root of 12. But when you multiply both of these, you get the square root of 96, which is not a non-perfect square root. And I think if you put it in your calculator, it's like 9.797 ... You don't have to do that as long as you know that 96 is not a perfect square root. So that makes it irrational. Kind of running out of room there, but you get the idea. So let's go ahead and pause the video and try number 7. So number 7 is 0, which is a rational number times an irrational number. And this was part of our always rules. We said anytime you multiply a rational times an irrational, it was always irrational. But I also said there was one exception. Because of the 0 property rule of multiplication, we know that anytime we multiply a number by 0, our answer is going to be 0. It doesn't matter if we're multiplying a rational or an irrational number. We know that 0 is rational, and the answer, no matter what the other factor is going to be 0. So if the answer is 0, the answer is rational. So this was one of those exceptions in our always rules. So this is actually 0. Which makes number 7 rational. All right, guys, we've got one more addition problem in there, number 8. If you want to take a minute, pause the video and try number 8, and then we'll come back and look at it together. So number 8 was in here to trick you guys, and I hope it didn't trick anybody. The answer to number 8 is not rational or irrational, because if you look at this first add-in, we are dividing by 0. And can we divide by 0? No, we cannot. 8 divided by 0 is undefined. If one of our terms is undefined, the entire problem is also undefined. So this is not rational or irrational. It is undefined. Hopefully that didn't trick anybody.